Introduction. Gas chromatography (GC) is one form of the more general separation process of chromatography. All forms of chromatography involve the distribution or partitioning of a compound between two different phases, one mobile and the other stationary. In GC, the mobile phase is an inert carrier gas, and the stationary phase is a high molecular weight liquid which is deposited either on the surface of finely divided particles or on the walls of a long capillary tubing. And the greater solubility in the stationary phase take longer to emerge from the bed than with the lesser solubility. Next, the concept of instrument in GC is first, sample injection. A sample pot is necessary for introducing the sample at the head of the column. Modern injection technique often employ the use of heated sample pot through which the sample can be injected and vaporized in a near simultaneous fashion. Second, carrier gas. The carrier gas plays an important role and varies in the GC use. Carrier gas must be dry, free of oxygen, and chemically inert mobile phase employed in gas chromatography. That is column oven. The thermostated oven serves to control the temperature of the column within a few tenths of a degree to conduct precise work. The oven can be operated in two manners. First is isothermal program, or second is temperature programming. The fourth is open tubular columns and packed columns. Open tubular columns, which are also known as capillary columns, come in two basic forms. The first is wall-coated open tubular, which is WCOT column, and the second type is a support-coated open tubular, SCOT column. Lastly is the detection system. The detector is a device located at the end of the column which provides a quantitative measurement of the components of the mixture as they elute in combination with the carrier gas.
So for the method of this experiment, there are three parts, part A, B and C. So for part A, preparation of the standard solution, number 1, 10 grams of ethanol was dispersed into 1000 milliliters polymetric flask. Separately, the distilled water was added to the flask until it reached the mark and the percentage weight over volume of standard solution ethanol were recorded. For part B, Trace GC operating system, number 1, Trace GC260 was equipped with computer integrated software and FID detector. The flow rate of both hydrogen gas and oxygen was set to 3000 milliliters per minute. And the temperature of FID detector and injection was set to 285 Celsius and 225 Celsius respectively. Both helium and nitrogen was set to 2 milliliters per minute and acted as a carrier gas. The CP-WES 58 CB separation column was used. The column temperature for wine and beer was set to 40 Celsius, while whiskey was set to 45 Celsius to 245 Celsius. The speedless injection mode was selected with a limitation of 0.1 microliter for whiskey solution, and for beer and wine, however, both was used in the split injection mode. So, part C, determination of alcohol content in alcoholic beverages. Number 1, standard solution ethanol was injected into the GC using a syringe. The peak for ethanol was observed and recorded. 5 milliliters of 1% weight over volume standard solution was added into the 0.5 milliliters of wine solution, and the solution was then swirled gently. The 0.1 microliter of the mixture solution was injected into the GC using a syringe, and the ethanol content was observed and recorded. Each analysis was repeated for 3 times for accurate reading, and the step 3 and step 6 was repeated by using a whiskey and beer solution.
Assalamualaikum warahmatullahi wabarakatuh. My name is AMIRAH SAKINAH binti SHAMSUL and my student ID is 2019333831. Today I'm going to cover a result part for experiment 5. So on the screen shows the figure 1 is result for ethanol. The graph shows the retention time taken for ethanol is 2.038 minutes, and the table shows the average percentage of alcoholic content for ethanol is none. Move on to figure 2 is result for beer. The graph shows the retention time taken for beer is 2.2 minutes, and the table shows the average percentage of alcoholic content for beer is 12.5%. Next is figure 3 is result for wine. The graph shows the retention time taken for wine is 2.3 minutes, and the table shows the average percentage of alcoholic content for wine is 16%. Lastly, figure 4 shows the result for whiskey. The graph shows the retention time taken for whiskey is 2.73 minutes, and the table shows the average percentage of alcoholic content for whiskey is 40%. Thank you.
Hi and Assalamualaikum. My name is Nurin binti YUSOFF. Today, I will be explain on discussion in experiment 5, which is gas chromatography. For discussion, gas chromatography is a good choice of method for analyzing alcohols as it focuses on analyzing volatile compounds. These substances can be analyzed using gas chromatography without any prior extractions. Ethanol is one of many volatile chemicals found in alcoholic beverages. 3 beverages were used, such as wine, beer, and whiskey. Detectors used is flame ionization detector or FID. It is good in detecting hydrocarbons. The capillary column serves as the stationary phase in this experiment, while the carrier gas nitrogen and helium serve as the mobile phase. Helium provides good efficiency and analyze time, but nitrogen is the best in providing good efficiency in gas chromatography. First, ethanol solution. To obtain ethanol retention, FID was employed in the experiment, which was set up at 240 degrees C and used Zebron ZB-BAC1 as the column or stationary phase. The temperature in the column is 40 degrees C. Helium gas is employed as the mobile phase with the flow rate of 2.57 ml per minute. Ethanol used is the lowest concentration to know the retention time of the ethanol and are used as the standard solution. The sample was injected in split mode and the retention time or TR after analysis was 2.038 minutes. Second, for 1, the detector used in FID to read the temperature of 240 degrees C by using Zebron ZB-BAC1 as the column or stationary phase. The column temperature is 40 degrees C. Helium gas is employed as the mobile phase with a flow rate of 2.57 ml per minute. Split mode is the injection mode for this experiment. Since the average percentage of alcohol content withdrawn for 1 is 16%, the retention time obtained is 2.3 minutes. Third, beer. Beer used the same setting as wine, with the use of Zebron ZB-BAC1 as the column or stationary phase. The experiment was set up at 240 degrees C utilizing FID. Helium was employed as the carrier gas with a flow rate of 25.7 ml per minute. The column temperature is 40 degrees C. The average percentage of alcohol content for beer is 12.5% when injecting the sample into the injection port in split mode. The retention time of beer is indicated as 2.2 minutes. Lastly, whiskey. Whiskey has the most alcohol content with 40% alcohol content with a flow rate of 2 ml per minute. It used epitels mode as the injection mode and nitrogen as the carrier gas or mobile phase. The temperature was set up step by step starting at 45 degrees C and increasing to 245 degrees C utilizing the polar CP-RES58 CB column or stationary phase. The detector was a FID and the temperature was adjusted at 285 degrees C. The average percentage of alcohol content in whiskey is 40%. The retention time was 2.73 minutes.
In the conclusion, the highest retention time, the higher the ethanol concentration in alcohol beverages. Therefore, the whiskey has the highest concentration of ethanol as it has the highest retention time, followed by wine. Lastly is the beer. The retention time for each and every solution are 2.73 minutes, 2.30 minutes, and 2.20 minutes respectively. The advantages of using gas chromatography, it has high efficiency. Due to its high efficiency, GC allows the separation of the component of complex mixture in a reasonable time. It is also has high sensitivity as GC has multiple detectors with high sensitivity which are flame ionization detector, thermal conductivity detector, and electron capture detector. Next, it has accurate quantitative and it is inexpensive compared to the HPLC. The limitation of using gas chromatography, it is very limited to terminal stable and volatile compounds or the result of the gas chromatography is not accurate. Lastly, the separated components can be used only once. The sample has been destroyed when it goes through the detector. Therefore, it cannot be analyzed for future research. That's all from us. Thank you. Bye.
Assalamualaikum warahmatullahi wabarakatuh. My name is AMIRAH Binti SHAMSUL and my student ID is 2019-333-831. Today I'm going to cover an introduction part for experiment 6. Caffeine is a natural alkaloid found around 60 plant species and it is a natural stimulant that are found in plants such as tea, coffee and cacao plants. The effect of caffeine is that it helps us to stay awake and prevent exhaustion by activating the brain and central nervous system. As it is a stimulant, it also can raise the heart rate and blood pressure, thus affecting someone's general health. There are many sources of caffeine such as brewed coffee, espresso, tea, chocolate and supplement. As for brewed coffee, 1 cup of brewed coffee contains about 95 mg of caffeine, and the same amount of instant coffee contains about 60 mg of caffeine. For espresso, 1 shot or 1.5 ounce contains about 65 mg of caffeine. For tea, 1 cup of black tea contains about 47 mg of caffeine. Green tea contains about 28 mg of caffeine. Decaffeinated tea contains about 2 mg and no for herbal tea. While for chocolates, 1 ounce of dark chocolates contains about 24 milligram of caffeine, whereas milk chocolate contains 1/4 of that amount. For supplements, caffeine contains about 2 milligram per tablet, or the amount in 2 cups of brewed coffee. Caffeine is most often used to increase mental alertness, but it also have variety of other application. For example, caffeine is used to treat migraine headache when taken orally or rectally, with pain relievers such as aspirin and acetaminophen with a substance called ergotamine. It also used in conjunction with pain relievers to treat and prevent a mild headache. Previous researchers have used several methods to determine the caffeine level in some beverage and non-beverage goods such as HPLC to determine caffeine level in cola soft drink and UV visible spectrophotometric to determine caffeine level in black coffee. Thank you.
Methodology. For the methodology, the sample preparation and analysis of the experiment HPLC, which is high performance liquid chromatography, have 3 parts that can be done, which is reading the HPLC for operation, separating paraben mixture, and analysis of caffeine beverage. The extracted sample also will determined by HPLC UV, which is high performance liquid chromatography ultraviolet. The analytical column was C18, UV wavelength was 259 nanometer, and the mobile phase was H2O, ethanol, acetic acid, run at flow rate of 1 ml per minute. So for the ready HPLC for operation, it can be done by ready the HPLC by making sure the solvent reservoirs are full and the waste bottles have at least 1 liter of volume available to accommodate the waste solvent. Then launch open lab by clicking HPLC1 and click on the HPLC1, which is online desktop icon. Next, use the instrument control tab. Confirm that all components are green and indicate ready. If this is not the case, press the on button. The DAD, diode array detection, will take a few minutes to warm up. If there is a lightning bolt through the purple lamp, wait until it has gone away and the ready bar has turned green. The fraction collector will not use in this experiment. Next, for the separating of paraben mixture, basically parabens are a class of chemical widely used as a preservative in the cosmetic and pharmaceutical industries. Parabens can be found in shampoos, shaving gels, personal lubricants, topical or parental pharmaceuticals, spray tanning lotion, and toothpaste. Parabens can also be used as food additive. Paraben mixtures are often used in order to increase the efficiency of preservation. Because parabens are often found in mixture, HPLC can be used to separate the individual compounds to determine the components in the mixture. Reverse phase, HPLC will be performed through a C18 column. C18 can simply mean that the molecule contains 18 carbon atoms, so the other atoms in the molecule can vary, leading to significantly different substances. Knowing the characteristic of the compounds that will be run through the C18 columns can help we choose which one will work best for us. So for this method, we have 2 samples that we need to run, which is preparing the standard caffeine samples and preparing the beverage samples. And lastly is preparing a sequence for the caffeine standards and samples. Last in this experiment is the treatment of data. We can print the reports after each run or after all runs are complete, and we also can find the data reports by clicking the data analysis tab in the bottom and create a calibration curve using the caffeine standard peak, height or area versus the concentration. Lastly, for the analysis of caffeine in beverage, reverse phase HPLC can be used to determine the amount of the caffeine in these items. In this experiment, we will be determining the amount of caffeine in coffee, tea, and a soft drink. If the runs are performed with the same isocratic parameters, retention time can be used as a qualitative measure, and peak area or peak height can be used as a quantitative measure of caffeine in the sample. In order to determine the concentration of caffeine in the sample, a calibration curve must be put together using a set of standard solutions comparing either the peak height or peak area to the known concentration of the solution.
Let's go through to the results we got from this experiment. So for figure 1, we got a chromatogram results of caffeine standard solution that has a retention time of 2.518 minutes. And figure 2, we got a chromatogram results of sample X that has a retention time of 2.058 minutes. For figure 3, we got a chromatogram result of sample Y that has a retention time of 2.491 minutes. And for figure 4, we got a chromatogram results of sample Z that has a retention time of 2.495 minutes.
In discussion, we went to discuss the data that we got from the experiment. Firstly is the quantitative test. The result of system suitability test obtained RSD of TR equal to 0.199%, RSD of AUC equal to 1.476%, and tailing factor equal to 0.67. This data showed that chromatographic system meets the requirements of RSD, TR, and AUC less than 2% and 0.5 less than TF less than 213. The result showed a linear relationship between the concentration of standard caffeine solution with the concentration range of 40 to 200 microgram per milliliter. The result was obtained linear regression equation y equals to 15044x plus 231298.87 with the R value equals to 0.992, which is in unit microgram per milliliter, and Y as AUC MV. Next, refer to the caffeine content of the 3 coffee beverage samples as listed in table 3. The caffeine content of the 3 coffee beverages samples are statistically different P less than 0.05. According to Indonesian Standard Agency, the allowed caffeine levels are 150 mg per day and 50 mg per servings. While based on the FDA, which is Food Drug Administration, the dose as caffeine is allowed for adults less than 400 mg per day. However, the present study showed that caffeine content does not comply with the SNI, wherein a serving should only contain a maximum of 50 mg of caffeine, while in samples X, Y, and Z, levels obtained are 132.048 mg per bottle, 109.699 mg per bottle, and 147.669 mg per bottle. Refer to the table 3. This level exceeds the limit set by Indonesian Standard Agency for 1 serving of coffee. Lastly, based on SNI 013542-2004, the limit of caffeine allowed to be consumed is 150 mg per day, while the FDA regulation allowed the level of caffeine less than 400 mg per day. Thank you.
Hi and Assalamualaikum. My name is NURUL Binti Yusoff. Today, I will be continue part of conclusion. In this experiment, the caffeine levels in samples X, Y, and Z was determined. The caffeine content of the X, Y, and Z coffee beverages samples respectively were 132.048 mg per bottle, 109.699 mg per bottle, and 147.669 mg per bottle. The levels of caffeine contained in the X, Y, and Z coffee beverages are not complete with Indonesian Standard Agency regulation. This is the references that we use for experiment 6. That's all for me. Thank you. Bye.